The evolution of message queues, from simple messaging to event streaming. Introduction. In the world of modern software architecture, message queues have undergone a remarkable transformation. What began as simple messaging systems have evolved into sophisticated event streaming platforms that power today's most scalable applications. Let's explore this evolution through 4 distinct generations of message queue technology. The foundation, traditional messaging middleware. Our journey begins with traditional messaging middleware, the first generation of message queuing systems. In this model, we see a straightforward approach where messaging middleware sits between applications, facilitating communication through dedicated queue managers. Each queue manager handles multiple queues, with messages flowing from sender applications through these managed queues to receiving applications. This architecture provided the foundational concept of asynchronous communication, allowing applications to send messages without waiting for immediate responses. However, this approach had limitations in terms of scalability and management complexity, as each queue required individual oversight and maintenance. The distributed revolution, RabbitMQ and message brokers. The second generation brought us distributed message brokers, exemplified by RabbitMQ. In this model, producers send messages to exchanges, which then intelligently route these messages to the appropriate queues based on predefined rules and routing keys. The exchange system provides flexibility in message distribution, whether broadcasting to multiple queues, routing based on specific criteria, or implementing complex messaging patterns. Multiple consumers can subscribe to different queues, enabling parallel processing and improved system scalability. This architecture solved many of the limitations of traditional messaging middleware by providing better load distribution, fault tolerance, and more sophisticated routing capabilities. The streaming era, Kafka and event-driven architecture. The third generation marked a paradigm shift with the introduction of Apache Kafka and event streaming platforms. Rather than treating messages as discrete units to be consumed and deleted, Kafka introduced the concept of persistent event streams. In this architecture, producers publish events to topics, which are then organized into partitions for scalability. Each partition maintains an ordered, immutable sequence of events that can be consumed by multiple consumer groups simultaneously. This approach enables not just real-time processing, but also the ability to replay events, maintain event history, and support complex event-driven architectures. The Kafka cluster model, with multiple brokers managing different topics and partitions, provides exceptional scalability and fault tolerance. Each broker can handle multiple topics and partitions, distributing the load across the cluster while maintaining data consistency and availability. The all-in-one solution, Pulsar and modern event streaming. The fourth and most recent generation is represented by Apache Pulsar, which takes an all-in-one approach to event streaming. Pulsar combines the best features of previous generations while addressing their limitations through a unique architecture. Pulsar separates serving and storage layers, with brokers handling message serving while Bookkeeper manages persistent storage. This separation allows for independent scaling of compute and storage resources, providing better resource utilization and cost efficiency. The system supports both traditional messaging patterns and modern event streaming use cases. Publishers can send messages to topics, which are then stored in Bookkeeper for durability and served to consumers by brokers. This architecture provides the reliability of traditional messaging systems with the scalability and features of modern event streaming platforms. Key evolutionary trends. Throughout this evolution, several key trends emerge. Scalability, from single queue systems to distributed clusters capable of handling millions of messages per second. Persistence, evolution from temporary message storage to persistent event streams that maintain historical data. Flexibility, from rigid point-to-point communication to flexible publish-subscribe patterns and complex routing. Fault tolerance, advancement from single points of failure to distributed resilient architectures. Real-time processing, growth from batch-oriented processing to real-time event streaming and processing. The impact on modern applications. This evolution has fundamentally changed how we build applications. Modern systems can now process events in real time while maintaining complete event history, scale horizontally across distributed infrastructure, implement complex event-driven architectures, provide better fault tolerance and disaster recovery, and support both traditional messaging and modern streaming use cases. Looking forward, the evolution of message queues reflects the broader transformation of software architecture toward distributed, event-driven systems. Each generation has built upon the previous, addressing limitations while introducing new capabilities. As we continue to build more complex distributed applications, these messaging systems remain the critical infrastructure that enable reliable, scalable communication between system components. The journey from simple queue managers to sophisticated event streaming platforms demonstrates how foundational technologies evolve to meet the changing needs of modern software development, enabling the reactive, real-time applications that define today's digital landscape.